Hello. I'm Hanlin, and well, it's a pity that I couldn't meet you in person. But anyway, let me present the result connecting the meta complexity of KT and parallel cryptography to you. This is a joint work with my advisor Rahul Santanam, and it was presented on last year's CCC. Let me start by presenting some backgrounds on both meta complexity and cryptography, and then we'll see how these two lines of research intersect each other. Meta complexity studies the complexity of computing complexity, and this is perhaps best illustrated by the minimum circuit size problem. Also, this minimum circuit size problem will be one of our motivations of this work. So let me introduce it to you. By circuits, we mean DACs with AND or NOT gates that compute some function. For example, here is a circuit that computes the XOR of two input bits. It has 5 gates. And the circuit complexity of a function is the size of the smallest circuit that computes it. In traditional complexity theory, we have some function of interest, such as satisfiability, and we want to prove circular bounds against this interesting function. In contrast, in the minimum circuit size problem, we are given an input function. We want to know the smallest. We want to know its circuit complexity. We want to compute its circuit complexity. So MCSP receives two inputs. The first input is the truth table of a function. If the function has n input bits, then the truth table has length 2 to the n. So you use 2 to the n bits to completely describe this function. And the second input of MCSP is a size parameter as you want to decide whether there is a size circuit that computes F. So this is the definition of MCSP. Is everything clear? If it's clear, I'll proceed. I see. Oh, I see someone in the chat. Marco said yes. Thank you. And what is known about the complexity of MCSP? So first, it's obvious that MCSP is in NP because you can simply guess a circuit and verify its truth table is indeed the given one. You need to be careful with your parameter here. Like the circuit has 2 to the n sides, and it takes probably 2 to the n time to verify your circuit computes the given truth table. But your impedance is already 2 to the n anyway. So this is indeed a non-deterministic polynomial time algorithm. Is MCSP easy? Competence and type proves that if MCSP is in polynomial time, then there are no one-way functions. In other words, if you believe the security of modern cryptography, then you should also believe MCSP is a hard problem. Now we have a problem in NP which we suspect is hard. It's natural to ask if it's NP complete. Oh, by the way, if you have any questions, feel free to interrupt me. So it's MCSP NP complete. This turns out to be a long-standing open question. Actually, it's said that Levin wanted to prove MCSP is NP complete, and this even delays his publication of his NP completeness results. Levin tried 1 or 2 years and failed to prove NP completeness of MCSP. And after 50 years, we still don't have a good answer on this problem. So the complexity of MCSP seems a big mystery in this sense. What makes it more mysterious is the following robustness question. Let's say we define MCSP over 2 different circuit models. Let's say 1 over AND or NOT and 1 over NAND. We don't know if the 2 versions of MCSP has any connection at all. So we haven't ruled out the case that one version of MCSP is super easy, but the other version is super hard. We simply don't know. It would be very interesting to give any non-trivial reductions between these 2 versions of MCSP. So this is what we know about the complexity of MCSP. it's kind of a mystery in some sense. We also need to introduce the time-bounded Kolmogorov complexity and its meta-complexity. I think Shruti also already gave us the definition of Kolmogorov complexity and time-bounded Kolmogorov complexity. So let me go through it quickly. For string x, kx is the length of the shortest program that computes x. For most strings that we can construct explicitly, it should have low Kolmogorov complexity. But on the other hand, a counting argument shows that a random string has high Kolmogorov complexity. So in some sense, Kolmogorov complexity measures the amount of randomness in a fixed string. Kolmogorov complexity is good, but it's not computable. So let's add a time bound on it. For a time bound t, k to the t of a string x is the length of the shortest program that computes x in t steps. Let's consider the scenario where t is a polynomial in the length of x. So computing k to the t is a problem in NP because you can guess a program and simulate it for t steps. Henceforth, we will call this notion k-poly. You should note that k-poly is not a rigorous notion because for different polynomials, k to the t might behave very differently. But in this talk, let's just call all of them k-poly for convenience. Similar as MCSP, it's also a big open question whether k-poly is NP hard. Okay, and now let me introduce the main character of this talk. It's called KT or K capital T complexity. This is a Kolmogorov version of circular complexity defined by Eric. Its definition is as follows, and let me explain it. To find the KT complexity of a string X, you need to find a program D. Here, U is just the universal Turing machine, and what you need to find is actually the program D. The program D should compute X in the following sense. Given any index I, the program D should output the X bit of X. So it treats X as a truth table. The complexity of this program D is defined as its description length plus its time complexity. So to find the KT complexity of a string, you minimize over all programs that computes X in this sense. You minimize the complexity of the program in this sense. It's not hard to see that KT of a truth table is polynomially related to its circular complexity. If you have this short and fast program that on input I outputs xi, then you can translate it into a circuit. And on the other hand, if you have a circuit, then you can translate it back to a program. Each translation only gives you like a polynomial overhead. So KT and circular complexity are polynomially related. And we can think of KT as a Kolmogorov version of circular complexity. The advantage of KT over circular complexity is that KT is sometimes more convenient to deal with. And this will also be the case in our talk. KT has the same situation as MCSP and k-poly. First, it's computable in NP. You just guess a program and verify it. Second, it's a big open question whether it's NP hard to compute KT. I think this is a natural question to pause and see if there are any questions. If there are no, then I'll continue. Okay, so I see a question. Oh, no questions. Oh, thank you, Marco. So I'll continue and introduce some background on crypto. I'll try to give a gentle introduction. I don't want to assume you have some knowledge on crypto. So the basic notion we will consider is one-way functions. It's arguably the single most fundamental concept in cryptography. It's already defined in the seminal work of Diffie and Hellman. So in case you don't know, in case you are not familiar with this concept, let me introduce it to you. So if a function f is one-way function if first given x, it is easy to compute its value fx, and second, given fx, it is computationally hard to compute x back. Notice that this hardness of inverting f is defined in an average case sense, and let me give you a precise definition. F is a one-way function if it's polynomial time computable, and for every polytime adversary A, the probability over a uniformly random x that if you feed fx to A, then A successfully inverts fx. This probability should be very small. It should be negligible in n, which means less than 1 over poly n for every polynomial. So let me emphasize that the hardness of inverting the one-way function is an average case hardness. If you are still not familiar with this concept, I can give you a candidate. Suppose you have x as input. You use x as random bits to sample two primes p and q, and you return the product of p and q. So this, if factoring is hard, then this seems like a reasonable candidate for one function. Why? Because if you want to compute fx from x, it's easy. You just do multiplication of two big numbers. But if you want to invert f, it seems that you need to factor this product of two primes, which looks hard. Hope this gives you some sense what a one-way function may look like. And so why do we say one-way functions are fundamental? In my opinion, there are two reasons. The first reason is that it's necessary for almost all cryptography. For almost all crypto primitive you can come up with. If a secure primitive exists, then it implies a secure one-way function. On the other hand, one-way functions are sufficient for a large fraction of crypto. Sometimes they are called mini-crypt. This is a partial list of mini-crypt primitives which are equivalent to one-way functions. And for this reason, for these two reasons, we think one-way functions are fundamental. Okay, so towards building secure cryptography, it's natural to ask, do one-way functions exist? Well, if we assume some problems are hard, we do get one-way functions. In this, for example, factoring discrete log and some lattice problems. These problems have structural properties such as worst case to average case reductions. So for example, if you just assume discrete log is hard in the worst case, then you use the worst case to average case reduction for discrete log, and you get one-way functions. It seems that set does not have such structural properties, so you don't get one-way functions assuming worst case hardness of set. Some skeptics may say perhaps this just means factoring is easy instead of the existence of one-way functions. Well, this is not an unreasonable skeptic because we don't have complexity theoretic evidence that factoring is hard. I think the most compelling evidence is simply that we haven't been able to find good algorithms. Perhaps someday a genius will come up with a very fast algorithm for factoring, and that breaks your crypto systems. So this motivates the problem of basing one-way functions from firm complexity assumptions, such as P not equal to NP. However, there are barriers for showing P not equal to NP implies one-way functions. For example, this cannot be done by black box non-adaptive reductions unless polynomial hierarchy collapses. So it seems that we need very new techniques to base one-way functions from, say, P not equal to NP. So are there any questions? If no, I'll continue. And this is the, okay. Thank you, Marco. So this is the intersection between meta complexity and crypto that I mentioned before. It's a very beautiful result by Liu-Pass. Liu Yanyi, who just gave the talk before me. Their paper is titled on one-way functions and Kolmogorov complexity. In this very beautiful paper, they showed that K-poly is hard on average if and only if one-way functions exist. So let me define what it means by K-poly being hard on average. Imagine a polytime heuristic which tries to compute K-poly. Given input x, it outputs a guess for k to the t of x. Here you can think of t as an arbitrary polynomial. The Liu-Pass result works for any well-behaved polynomial. I call this thing a heuristic instead of an algorithm because we allow it to make some error. We say K-poly is bounded error hard on average if there is an absolute constant C such that for every polytime heuristic A, if we feed a random x, uniformly random x to this A, then the probability that A outputs k to the t of x correctly is at most 1 minus 1 over n to c. So this is the definition of K-poly being bounded error hard on average. Liu and Pass shows that this is also equivalent to the existence of one-way functions. This is a very nice and elegant characterization. It captures the central crypto primitive one-way function by the complexity of a very natural problem, K-poly over the uniform distribution. And I think this is a very fundamental link between meta complexity and cryptography. In some sense, this also bases crypto on the firmest possible complexity assumptions. First, this is a characterization. And second, if you want to investigate the existence of one-way functions, you just need to link the average case complexity of K-poly to other notions of in complexity theory. So this is the Liu-Pass result. And before going into our results, I want you to keep in mind some motivations of this work. Liu and Pass showed that one-way functions correspond to hardness of K-poly. But why is it K-poly? Why can't it be MCSP, or can it be MCSP? This is one of the motivations of our results. And maybe I should pause again and see if there are questions. If no, then let me show you our results. Our first result is the following. KT is hard on average if and only if there exists one-way functions in uniform NC0. So this result, is there, does my pad lag before my voice? Okay. I see. Thank you. Thank you. My internet was unstable just before. So my first result is that KT is hard on average if and only if there exists one-way functions in uniform NC0. So it turns out that KT also characterizes some natural crypto problem. I will tell you what NC0 means if you don't know. And I should also justify that one-way functions in NC0 is a natural crypto problem. NC0 is a class of multi-output functions where each output bit only depends on a constant number of input bits. You can think of it as functions computed in constant parallel time. Each output bit can be computed in constant time. So this is an extremely simple class. So one-way functions in NC0 means the functions where the easy way is super easy, but the hard way is still super polynomially hard. Given the very simple definition of NC0, you may wonder if there are any one-way functions in NC0 at all. This question was essentially resolved by a breakthrough work of AIK. AIK showed that one-way functions computable in NC1 or even log space implies one-way functions computable in NC0. Here, let me give you a figure about the hierarchy of this complexity classes. On the bottom, you can see NC0, and then it's AC0, which is a slightly more powerful class, and then it's DC0, NC1 log space, and so on. So you can see where this NC1 and log space lies in this hierarchy. AIK shows that one-way functions here can be somehow compiled into one-way functions here. In particular, it shows a white box compiler. Given the code of a log space computable one-way function, it compiles the one-way function into another one-way function computable in NC0. The hardness of the new one-way function is approximately preserved. So a corollary of this result is that NC0 one-way functions follow from most standard crypto assumptions. For example, discrete log. If you assume discrete log is hard, then you get a one-way function whose computation is just like picking some field elements and doing some exponentiation. This can be done in NC1. So you get one-way functions computable in NC1. You apply the AIK compiler to, and then you get one-way functions in NC0. This also justifies my assertion that crypto in NC0 is a supernatural problem to consider, because it's basically equivalent to crypto in any low enough complexity class, be it TC0 or NC1 or log space. So here is a summary slide of our main result. NC0 is a super easy class. It's the class of multi-output functions computable in constant parallel time. NC0 one-way functions are widely believed to exist because they are also equivalent to one-way functions in log space. And KT is this notion. It's the Kolmogorov variant of circular complexity. It's just circular complexity, but technically somewhat more convenient than circular complexity. And our first result is that KT is hard on average if and only if there exists one-way functions in uniform NC0. I guess now it's time to pause and see if there are questions. Okay, then let me proceed to show you our second result. Oh yeah, yeah. Please ask. Liu-Pass showed one-way functions are also equivalent to hardness of additive approximating K-poly. The additive gap is C log n, I think. It's O log n for any constant C. And this also applies to our results. KT is average case hard to approximate within additive error C log n if and only if there are one-way functions in NC0. Also, if and only if KT is hard on average to exactly compute. So we have some, so Liu-Pass is some gap creating reduction. It says if K-poly is hard to exactly compute, then K-poly is also hard to approximate. Same as our result. And thank you for the question. If there are no other questions, I'll introduce our second result. So our second result is we treat AIK as a reduction between meta-complexity problems. I actually like this result very much. So let's think about the Liu-Pass result. They prove that hardness of K-poly is equivalent to the existence of one-way functions. But if you dig into the argument a little bit, they also prove that hardness of C K-poly is equivalent to one-way functions computable in C for reasonable circular classes C. Well, I didn't define CK poly, and I won't do it in this talk. If you follow the argument of Liu-Pass, you can get some good definition of CK poly that makes this statement true. Okay, and if you also think about AIK says one-way functions in NC1 is equivalent to one-way functions in NC0. If you add them together, it says hardness of NC1 K poly is equivalent to hardness of NC0 K poly. For now, let's think of NC0 K poly is roughly equivalent to KT. They are actually quite different, but they are essentially the same for the purpose of our second result. So we get that NC1 K poly and KT are equally hard on average. Is there any reduction between them? Our second result shows the answer is yes. We interpret the techniques of AIK as a reduction between NC1 K poly and KT. We show there is a randomized reduction that maps a random instance to a random instance and maps an instance with small NC1 K poly to an instance with small KT. So unfortunately, we don't know if this is a worst case reduction, but at least it's an average case reduction from NC1 K poly to KT. Some remarks. First, it also works for log space K poly. The only property of NC1 that we use is AIK works for NC1. If AIK works for some class, then our reduction also works for the same class. So if AIK works for polynomial time, say if they prove one-way function imply one-way function in NC0, then we could reduce the standard K poly to KT. What I found remarkable about this result is that it connects the complexity of two different meta-complexity notions. As I mentioned before, we don't have much robustness results for meta-complexity, at least before this work. So we don't know if the two different versions of MCSP are equivalent. We don't know reductions between them. And we also don't know if K poly and KT has any connection at all. In this result, we built the first reduction between some variant of K poly and KT. So this is what I find remarkable about this result. Another remarkable property is it also works in the zero error regime. So if you recall the definition of one-way function, it's inherently about bounded error or error-prone heuristics. But this reduction, it turns out it also works for zero error or errorless heuristics. So if KT is zero error easy on average, then so are NC1 K poly and log space K poly. So if you work out what's actually going on for AIK, Pericles said, I believe there is a follow-up of AIK. Where under standard assumptions, they show how to compare every P function in NC0. Are you referring to the computational randomized encoding paper? Sorry, I haven't heard about that paper. I only know there's a CCC paper also by AIK, which shows, I think under some crypto assumptions, every polytime computer function has computational randomized encoding. But that paper doesn't seem to give new results in our context. Maybe we can discuss it offline. Thank you. And so let me also have one slide for MCSP. Recall our motivation was actually for MCSP. We want to show average case hardness of MCSP is equivalent to one-way functions in some way. It turns out that circuit complexity is messier to deal with than KT complexity. So we can still prove non-trivial theorems, but not as are not as clean as KT. We show if MCSP is exponentially hard on average, then there is a super poly hard one-way function. For comparison, the result for KT is much cleaner. If KT is super poly hard on average, then there is a super poly one-way function in NC0. This one-way function, we don't even know how to implement it in NC0 or any low enough complexity class. At least currently, I don't know. We also have a partial converse. If there is an exponentially hard one-way function in NC0, then MCSP is exponentially hard on average. This result for MCSP does not extend to super poly hardness. It requires exponential hardness. Anyway, the takeaway message for this slide is that using similar techniques, we can prove something non-trivial for MCSP, but because circular complexity is somehow harder to deal with, we don't get full equivalences. And okay, and actually that's all I want to present today. Thank you for your attention. And any questions are welcome.